Okay, welcome to the lecture 59 in this course, Classical Mechanics 1. And in last few lectures, we were discussing the small oscillation. And you remember in the last class, we were discussing a coupled pendulum and its normal modes and normal frequency. To remind you, let me draw the pendulum again. So, it was a pendulum, two simple pendulum and connected by a spring of spring constant k, and the mass of the each pendulum was m, and this length was L. Okay. So, and we obtain the Lagrangian of this system, and then we find the normal modes. And if you recall, the normal modes was found by solving that v minus omega square t determinant equal to 0, and we find omega 1 was g by L and omega 2 was g by L plus 2k by m. Okay. So, this frequency we calculate, and then now we will calculate what will be the eigenfunction corresponding to these frequencies. So, eigenfunctions for these frequencies. So, let us first calculate this eigenfunction for this. So, for that we will have okay, so let us denote say for example, when omega L, let me denote the frequency as okay, so omega 1 will denote the eigenvector eta 1 as a11 and a21. My notation is that I am denoting a L j L for the eigenvectors for omega L. Okay. So, L equal to 1, so both places 1, and j will be sum for the how many frequencies we have. Similarly, for the omega equal to omega 2, eigenvector will be eta 2 equal to, so in this case L will be 2, so a 2 and j will be summed, so 1 and 2 2. So, let us calculate this eigenvectors first, and then we will consider a general eigenvector for a general problem with n degrees of system, how to find this. Okay. So, for that purpose, let us recall our determinant matrix was G by L plus K by M minus omega 1 square. For omega 1 frequency, we can write minus K by M and G by L K plus M minus omega 1 square, and this eta 1 eigenvector. So, 2 1 should be 0. Okay. And you solve this equation for omega 1. So, omega 1, recall omega 1 is root G by L. So, omega 1 and this will get cancelled. So, this will cancel with this for this case, this will cancel with this. So, you will left with K by M minus K by M minus K by M plus K by M. Okay. And a11, a21 will be 0. And if you solve, you will find that your a11 equal to a21. So, eta matrix, eta 1 the eigen function, you can write a11, a11. So, that is a11, 11. And there is no way to find here at this moment to find it will be a11, but we will see that in a general framework that we can normalize these eigenvectors to find this constant a11. Similarly, for if you consider omega 2 equal to the eigenfunction g by L plus 2k by m, so this eigenvector, then the corresponding equation, if you substitute omega 2 here, and you will find or let me write g by L plus k by m minus omega 2 square minus k by m minus k by m minus g by L plus k by m minus omega 2 square, with the 1 2 and a 2 2 eigenvector will be 0. So if you have this one, then substituting omega 2, you will get minus k by m minus k by m, because this omega 2 has 2k by m and minus, so okay, so this 1 2 and a 2 2 will be 0. So if you solve this, you will get, a 1 2 will be minus of a 2 2. So the eta 2, so eta 2 eigenvector, you will get a 1 2 times 1 minus 1. Okay. So let me summarize here that eigenvectors for omega 1 frequency, eigenfrequency, which is g by L, your eigenvector is eta 1, which is a 1 1 1 1, and omega 2, which is root g by L plus 2k by m, eta 2 equal to a 1 2 1 minus 1. Okay. So we'll come back to this, and at this moment you can find that eta 1 dot eta 2 is 0, because if you have 1 1 matrix multiplying 1 minus 1, it will be 0. a 1 1 a 1 2 are outside. Okay. So this are the orthogonal. So eta 1 and eta 2 orthogonal. Okay. So these are known as normal modes. Okay. And later we will see how this can be normalized, these modes can be normalized. Okay. So for that we have to go back to the general consideration. You recall the general consideration when we write down the equation of motion and then we substitute the oscillatory solution. You recall that we obtain the equation in terms of the V and T matrices. Let me recall that V j k minus omega square T j k q j equal to 0, and your q j, you remember q j was a j e to the power I omega t plus minus delta j. So this was the solution, and if you substitute this, if you write this equation in terms of by substituting q, you will get the equation j as v j k minus omega square t j k in terms of the amplitude a j equal to 0. So this a j is amplitude, and this is the phase. Okay. So what will happen that And the solution of this equation can be obtained when we have the determinant of Vjk minus omega square T jk will be 0. Okay. But what happened that I already mentioned that this eigenvectors corresponding to different eigenfrequencies are not normalized. So, we want to find a rule how to normalize this. Okay. So, for that purpose, let us write this equation for two different frequencies for omega equal to omega L, and for that our notation for the coefficients in the eigenvector will be A J L, and when omega equal to omega m, our notation will be A J M. Okay. So, let us explicitly write this equation in terms of explicitly in terms of this. So, J, or let me write with the different index k, V J k A k L. Okay, I am writing for this. Okay, so that is why my coefficient A k L and sum over k is equal to omega square sum over k T j k A k L. Okay. So, let us denote today this is equation number 1, and sum over j, when I write this equation for omega equal to omega m. So, V j k A j m. Okay. And this is omega square sum over j T j k A j m. So, let us denote this with equation 2. Now, if we multiply, now we will play with these two equations. If we multiply equation 1 with A j m and then sum over j, we obtain from equation 1. So, sum over j, so sum over j and k, V j k A k L A j m, okay, equal to omega square k j T j k A k L A j m. So, let us denote as equation 3, and equation 2, just let me little bit down, equation 2 we multiplied with A k L and then sum over k. So, what we obtain? Sum over, again see this is already sum over j and sum over k, so j k and V j k A j m A k L equal to, so this is your omega L, I forgot. So, this is omega m square sum over j k T j k A j m A k L. So, let us denote this is equation 4. So, we have done nothing, we just had two equation and for omega L and omega m, and that two equation we have written with some mathematical adjustment. That first equation we multiplied with AJM and then sum over j, second equation we multiplied AKL and then sum over k, and then we obtained equation 3 and 4. Okay. So, now if we subtract the equation 4 from equation 3, so equation 3 minus equation 4, you will get 0 equal to this is your omega L. So, omega L square minus omega m square, then sum over j k t j k a k l a j m. The left hand side are equal, so right hand side is different because they are different frequency. Okay. So, what happened that we write this equation. So, let us denote this as the equation 5. Okay. So, equation 5 will have that general equation. So, let us analyze this equation 5. So, equation when L equal to not equal to M. So, case 1 when L not equal to M, then we will have this cannot be 0. So, implies sum over T j k a k l a j m j k will be 0. Okay. So, this equation is orthogonality condition. Okay. So, let us write this as equation 6, and when L equal to M, the case 2, then this first factor cannot first factor equal to 0. So, second factor cannot be equal to 0. So, j k t j k a k l a j m not equal to 0, but it cannot be determined from this consideration. And here we consider that this is normalization of the eigenvectors such that t j k sum over j k t j k a k l a j m equal to 1. So, we normalize this equation to this and denote this as equation 7. Okay. So, if we combine this equation 6 and 7, we get j k equal to delta L m. So, when equation 8. So, when L and M are equal, you will get 1, and when they are different, you will get 0. So, that will be the your equation. And this equation, using this equation, we can calculate our this normalization. See vectors A11 and see remember our eta 1 was A111 and eta 2 we at the beginning we derive 1 2 is 1 minus 1. Okay. And in this coupled pendulum case, you have that T matrix. You recall T matrix was M L square 0 0 M L square. Okay. So, this using this T matrix, using equation 8, we can find A11 or A21 to find completely eta 1 and eta 2. Once eta 1 and eta 2 is found, then we can immediately find our complete solution, the normal modes. Okay. So, let us do that. So, for let us omega equal to omega 1 case. So, so our L equal to 1 in this case, and we want to use equation normalization equation of equation 8. So, let us consider M equal to 1, then right hand side will be 1. So, we will have sum over j k t j k a Now L equal to 1, M equal to 1, so K 1 and A J 1, and this is equal to 1. Remember, my T matrix is only diagonal matrix, okay. So I can expand this for this summation over jk. Jk are all values 1 and 2, 1 and 2. So it will be 1 1 a 1 1 square plus a 2 t 2 2 a 2 1 square. Remember, a 1 1 equal to a 2 1. That when we calculate this, we obtain this eigenvector eta 1. So this is equal to 1 implies a11 square times 2ml square equal to 1. So a11 we obtain 1 over 2 ml square times, okay, that is fine. So eta 1, so eta 1 we find 1 over root 2 m L square times 1 1. Exactly similarly, when omega equal to omega 2, that means our L equal to 2, and to use the normalization equation in the equation 8, m also has to be 2. So L equal to 2, m equal to 2 case, we will have sum over jk t jk a k 2 a j 2 equal to 1, and if we break this sum, you will get t 1 1 a 1 2 square plus t 2 2 a 1 2 square. Remember that a 1 2 was minus a 2 2. Okay, so I am writing everything in terms of a 1 1. So what will happen? We will get this as same normalization. A1 square will be 2m L square. So we found our eta 2 is 1 over 2m L square 1 minus 1. Okay. So this normalization condition, how to use and how to find. Also, when you will next lecture, when we will consider that linear carbon dioxide molecule, and that this small oscillation technique can be used to find the vibration in the linear carbon dioxide molecule. We calculate this normalization. So now we have explicitly found our eigenvectors. So normal modes so for omega equal to omega 1, we find that solution qt. So let us write q1 in this case. This one is different with earlier. So this as 1 over root 2 m L square, and then you will have cos omega 1 t minus delta 1 plus cos omega 2 t minus delta 2. Remember, in the first eigenvector we have 1 and 1, so that is why there is a plus sign. Okay. So for normal modes for omega equal to omega 2, this frequency will denote as q2t. So it will be 2m L square cos omega 1 t minus delta 1 minus cos omega 2 t minus delta 2 . Okay. So these are the complete solution. So now I'll explain little bit the physically what is the meaning of normal modes, and then the only remaining topic in this course will be the vibration of carbon dioxide molecules, that we'll discuss in next lectures. Okay, so normal modes and normal frequency. Okay, suppose you have a Lagrangian of this kind, half m x dot square plus y dot square minus half k x square plus y square. Okay, and we know this is a two-dimensional, this we know this is a two-dimensional decoupled simple harmonic oscillator. That means if I diagrammatically draw, suppose axis x and y, you will have a oscillatory motion and along x direction with frequency say k by m. Similarly, you will have oscillatory motion along y direction with root k by m, and they are completely independent. That is why I wrote decoupled. So if I changes the oscillation motion changes in x direction, it will not do anything to the y direction. So they don't talk each other. So they are decoupled, and you can call them normal modes. But if our Lagrangian contains a term say like minus alpha xy, then you will have this is 2D coupled system. Okay, and coupled by this term x and y. So your x variable will if we change in your x variable, the motion in the y direction also will change. Okay, so what will happen? So this is called coupled oscillation. So if we again draw, so then the oscillation in the x direction and oscillation in the y direction, they coupled each other through that coupling term. Okay, so what happened that in such cases we look for the normal mode solution. So how we mean that? Suppose we find not x and y direction, but say a capital X and capital Y direction. So suppose this is capital X and capital Y in such a manner that my Lagrangian in terms of capital X, capital Y, x dot, y dot will be half m x dot square, y dot square minus half k1 x square minus half k2 y square. Now you have different frequencies k1 and k2. If it is possible, then we can think of that this system will have oscillation along capital X direction and oscillation along capital Y direction are independent, because in terms of capital X and capital Y there is no coupling term. Okay, so then these capital X and capital Y are known as normal coordinates, and corresponding capital omega, this omega x, capital X will be root k1 by m, and omega y will be k2 by m will be the normal frequencies. Okay, so in this case we find that so it is possible to find a two independent direction for a two-dimensional system, say where will the frequency in one direction will not talk to the frequency in the oscillation in one direction will not talk to the oscillation in the other direction. Those are known. Okay, so this is all about normal modes and normal coordinates. In next class we will consider the vibration of linear carbon dioxide molecules. Okay, Okay, bye for now.